Alright, silly people, here's the situation. We have a particle that is falling, um, subject to the usual gravitational potential energy, um, but also subject to a frictional force, um, given by a dissipation force, fancy F, equal to k v squared over 2. And we're meant to find the velocity of the particle as a function of the acceleration and physical constants therein. Um, Using just the Euler-Lagrange equation and the definition of a generalized force, um, which is due to a dissipation function minus del f del q dot. So let's just get into it. We need to construct a Lagrangian as usual. So t is going to be your usual mx dot squared over 2. Uh, I'm just going to use x all the way through this equation because it's all one-dimensional. The potential uh, is just going to be mgx. Um, and so the Lagrangian will be t minus v, which is mx dot squared over 2 minus mgx. Nothing too crazy there. Uh, let's look at what qj is by noticing that the v in the dissipation function is one-dimensional and will also be just k x dot squared over 2, to put it in terms which are consistent with our dimensions. If we take the partial derivative of that with respect to x dot, you'll find that the generalized force will be it'll be k x dot. Okay, so that's the right hand side of the Euler-Lagrange equation. We still need to do the left side. So first I'm going to take a partial derivative of the Lagrangian with respect to x dot, which will be simply mx dot, and then the partial derivative of it with respect to x will be just minus mg, and then with respect to, if you take the time derivative now of the velocity derivative, you just have mx two dots. Now we can write the whole Euler-Lagrange equation, which is mx two dots minus, or plus mg now, plus mg equals m, or no, it's equal to minus kx dot. Okay. If you just solve for x dot, you just have m over k x dot plus x2 dot plus g, with a minus sign thrown on there for fun, equals x dot. You can solve that differential equation if you'd like to. I'm not going to. I'm just going to leave it like that. So now we need to look at what the maximum velocity for this system could be. If you think about it, you're just looking at a particle that's accelerating towards the ground until it reaches a terminal velocity. Once it reaches the terminal velocity, the velocity can't change anymore, so x2 dot will be equal to 0. So plugging that into our equation of motion, we have minus m over k times g is equal to v max, which minus mg. So that's okay. That's actually x dot max, if you want to be technical about it. But the absolute value of x dot max will be equal to the magnitude v max, which is going to be mg over k, which I think that's what Goldstein wanted us to find.